Hi, so this is your second set of notes for Unit 7. It's on shifts or exponential functions. We are going to talk a lot today about this d value. Remember that our exponential functions will have this form, f of x equals a times b to the x plus d. Remember that a is going to stretch or compress the function vertically. Okay, A is also going to be responsible for reflections over the x-axis. This is what we're going to talk about today. The d value is going to shift the function up and down, just like k did for quadratics, like k, and it tells the truth, again, like k, and b is still the base. Remember that b is the same as the common ratio, the pattern that we multiply by. Okay. So here we have to use the table to graph this function, and then we are going to identify its key characteristics. So what we are going to do is take 4 to the x and make a table for just the 4 to the x part, and then we're going to talk about the minus 5, because we know that that minus 5 is going to shift the whole thing down 5 units, because this is the d, okay, this is b to the x, right? So it's multiplying by 4, and it's shifted down 5 units. So instead of doing f of x, we're just going to do 4 to the x, and then we're going to worry about the minus 5. So x is going to be our usual suspects, -2, -1, 0, 1, and 2. So I'll have 4 to the -2, 4 to the -1, 4 to the 0, 4 to the 1, and 4 squared. Now I'm going to simplify those. So I'm going to start in the middle with my 4 to the 0, which is anything to the 0 power is 1. 4 to the first is 4. 4 squared is 16. Okay, now I'm going to use my flips. Okay, so 4 to the -1 is 4 to the +1 flipped upside down, the reciprocal. So this is going to be 1 over 4. And 4 to the -2 is going to be 4 squared flipped reciprocal upside down. 1 over 16. Okay, so here is the important thing. When we graphed our parent, we put the horizontal asymptote, here I'll draw it. We put the horizontal asymptote right here on the line y equals 0. But now we are going to shift our function down 5 units. So the asymptote is going to drop down 5 units. Chunk, 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 chunk. Okay, so I'm going to grab it and I'm going to drop it down 5 units. So you'll just draw it with your ruler, shifted down 5. Okay, I'm going to put my arrows on it. Now from this horizontal asymptote, I'm going to graph these pretending like it's my x-axis. So I'm not going to graph from my x-axis, I'm going to graph up from my asymptote. Okay, bear with me. So I'm going to leave my y-axis normal, it's not moving, but I'm going to pretend like my x-axis has dropped. Okay, so for my 0, 1, I'm going to go 1 up from my horizontal asymptote. Instead of going here, I'm going to go there. That's what we're doing. Okay, now from my horizontal asymptote and the y-axis, I'm going to go 1 right and up 4. So 1, 2, 3, 4, right there. From my y-intercept, y-axis and my horizontal asymptote, I'm going to go 2 right and up 16. 1, 2, 3, 4, 5, 6. Oops, did I go down 6? I did. Oh, shoot. I couldn't see my numbers. All right, guys, bear with me. This, it should be right there. Okay, this should be there. This should be up 4, right there. Sorry, your math teacher can't count. Okay, now I'm going to go up 16. So I'm going to go right 2 from the intersection, right 2 and up 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It should be right up there. It doesn't fit, but it's close enough. Good enough for rock and roll, as they say. Okay, and then I'm going to go left 1 and up a 4th. Okay, I'm going to go left 2 and up a 16th. So I'm getting very, very close to my horizontal asymptote. And this is the graph, guys. It's the parent just shifted down 5 units. Okay? So my y-intercept for the parent would have been 0, 1, but it's moved down 5 units. So it is now at 0, -4. So it would have been 0, 1, but we shifted it down 5, so it went to -4. Okay, the horizontal asymptote is now the line y equals -5. Y equals -5. Notice that it matches my shift. Okay, this is still growth. Remember that we read it going left to right. The domain is still all real numbers. Now my y values can't be under -5. They all have to be bigger than -5. And it can't equal -5 either because that's where my horizontal asymptote is. So my y's are greater than -5. So now I have to, for part B, describe the transformations of my function compared to my parent function. So all we did, there was no vertical stretch, there was no rocks. All we did was a shift down 5 units. That's it. The next one we'll do tomorrow is reflections, and then after that we'll do vertical stretches and compressions. But for right now, we're just shifting up and down. Okay, I'm a nerd. Okay, so example 2 says, write the equation of an exponential function with a base of 3 and a y-intercept of 4. So let's start with a little table. Let's start with the parent with a base of 3. So if I have a parent with a base of 3, here's my x's, here are my y's. So -2, -1, 0, 1, 2, okay? And my y's are going to be, we'll start with 0. Anything to the 0 power is 1. 3 to the first power is 3. 3 squared is 9, right? Okay, and then remember these are the flippers. So if I flip the first power upside down, I get 1/3. If I flip the second power upside down, I get 1/9. Okay, so those are the points for the parent function. And you can see right here is my y-intercept. But I don't want that to be 1, I want it to be 4. So how much do I have to shift my function up to get 0, 1 to become 0, 4? How do I turn a 1 into a 4? Well, I have to add 3. I have to shift it up 3 units. So it's going to be f of x equals 3 to the x, that's the parent, but I have to add 4. Whoops, sorry, we said 3, wasn't it? We have to add 3 because it starts at 1, the y-intercept, and it goes up 3 more to go to 4. Okay, now we have to write the equation of a different exponential function that has the same base as my answer from part A. So I want my base to match. This is my base. Okay, so it's going to be f of x equals 3 to the x, and then I can put whatever d value I want on there. I can put plus 0, I can put plus 1, minus 5, whatever you want. Plus whatever you want. All right, I'm going to put plus 2. And that's it. These just have to match the bases, same base. All right, here we go. Oh, yay, it's the return of the same and different problem. Woo-hoo-hoo. We already know how to do this problem. We did it with quadratics. It's just the same thing, but different. Got something weird going on. Okay, so I've got function 1 and function 2, and I have to compare them on this guy. So I'm going to make a table. I'm going to make a table of this parent, and then I'm going to shift it up 2 units because it's got a D of 2. So this is a shift up 2 units. Okay, so let's make a table. Here's my x's, and here is 1/2 to the x. I'm not going to call this my y because it's not my end result. I'm just doing the parent right now, and then we'll shift the parent. So -2, -1, 0, 1, 2. So if I have 1/2 to the -2, 1/2 to the -1, 1/2, ooh, that looks like crap. Maybe better. 1/2 to the 0, 1/2 to the first, and 1/2 squared. Okay, I'm going to start at the middle because that's what I know the answer to. Anything to the 0 power is 1. 1/2 to the first power is 1/2. 1/2 squared is 1/4. Okay, now I'm going to use my flippers. My -1 power flips my first power upside down. So that's 2. My -2 power flips my 2 power upside down. So that's 4. Okay, now I'm going to put my horizontal asymptote on there where it belongs. The parent horizontal asymptote would be here. But I'm not going to leave it there. I have to shift it up 2 units. So I'm going to go boop, 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 and shift it up. Okay, now I'm going to graph pretending like this is my origin. Okay, so from that point, I'm going to do these coordinates. So I'll do that in blue. So I go right or left 0 and up 1 from my new origin, my fake origin. Okay, left 1 up 2, left 2 up 4. Ooh, barely fits. Okay, and then right 1 up 1/2 from my asymptote, and right 2 up 1/4. So this is my graph. So there's also some information that we need from the other graph. We need to know the base for the other graph, right? So for this original graph that was graphed, we can pick 2 pretty points. So I'm going to pick this one and this one. Make me a table. So that's -1, 2. And that's 0, 1. So going from 2 to 1, I am multiplying by 1/2. So 1/2 is my R. Oops. Sorry, I forgot to write R. R is 1/2 and is also my base. So if you look at this, my bases, they match. They're both 1/2. So for base, I'm going to put same. For y-intercept, I can tell that those are different. They're crossing the y-axis in 2 different spots. They are both decay, so that's the same. The domain for both is all real numbers, so that's the same. The range, that's different. For my little pink stuff down here, it's y values that are greater than 0. Y is greater than 0. That's my range. For my blue one, it's y's that are greater than 2, because it all is above 2. So these are different, and the horizontal asymptotes are different. Ta-da! Okay. So when I look at this, I can tell just by looking at these functions which ones are going to be decay and which ones are going to be growth. So that one has a base of 3, so it's multiplying by 3. If it's multiplying by 3, it's going to be getting bigger, so it is going to be a growth. Okay? B is multiplying by 1/3, so it's going to be decay. C is multiplying by 3, so it's going to be growth. And D is multiplying by 1/3, so it's going to be decay. Now look at C and D. They are both shifted down because they both have a D of -2. So this is shifted down and this is shifted down. So now we can match them up. For A, we're looking for one that has growth but is not shifted. So this one is growth, but look, it's shifted down 2 units. This one over here is growth, but it's not shifted. The horizontal asymptote is right here, as opposed to this one, which is right here. You see the difference? So this is A. Now the other one that's growth is C, and that one does have a shift. So this has to be C. Okay, look at B and D. So they're almost the same, except this one is not shifted, and this one is shifted down. So this has to be D, and this has to be B. Okay, if you need help with that, come talk to me. Okay, almost done. The population of bacteria, P of T, in a culture is an exponential function of the number of T days and can be represented by the function P of T equals 100 times 3/2 to the T power. What is the population of bacteria on the second day? So this is what we're given. We're given T and P of T. So this is like the X, and this is like the F of X, or the Y, with a promise that it's a function. Okay? So for the second day, that's telling us that the T, which is the days, is 2. So if I plug in a T, what is the output? What is the population on the second day? So all I have to do is plug in a T. Okay, all I have to do is plug in a 2 wherever I see a T. So I say P of 2 equals 100 times 3 divided by 2 in parentheses, power caret 2. And I'm going to put that in my calculator. I'm going to put this part in my calculator. I don't need to put this part in. I just want the output for that expression. Okay, so calculator time. 100 times 3 divided by 2, close parentheses, power caret 2. I'm getting 225. So I'm getting that P of 2 is 225 what? Bacteria? Okay, another way would be to put this function in your calculator and look at your table. So I could go to my calculator, again, go to y equals, clear out whatever's in there, and do 100, open parentheses, 3 divided by 2, close them, power caret, and put an x. I know that the question says t, but your calculator is using x and y, which we've said is fine. And then I go to my table, and you can see that right here, when my t is 2, I do in fact get 225 for my output. So you can either manually type it in with the 2 on your calculator, or you can go and put it in your calculator and check out your table, and then you can see all kinds of outputs at the same time. So if you were saying, oh, on what day was the output, 150, you'd be like, oh, on day 1. Just saying. You get a lot of information from the table. All right, that's the end. That's all she wrote. Kids are going to start coming in.